Students, in this video, we'll see an example of finding a complex potential and using it to find the streamlines of a particular incompressible irrotational flow. So let's recall our typical setup. Our typical setup is given a velocity field u of xy, v of xy, that is incompressible or sourceless, and irrotational, then we can form g of z, which is u of xy plus I v of xy. We form this complex velocity, okay? Then this function is anti-holomorphic. Like that. Beautiful. And there's a complex potential, right? And there's a complex potential, g capital prime of z is g of z bar is holomorphic. And that implies that the imaginary part of g constant are the streamlines of the flow. Okay. What are some classic examples of this? Okay, so let's think about some classic examples. All right, so here's the first classic example. Example number 1. Let's consider g of z bar is equal to a constant k. A constant, right? That's definitely holomorphic, right? A constant. Okay. Well, in this case, what's the g of z prime? Then the g of z is just going to be what? It's just going to be kz, right? Just integrate that out and get kz plus another constant maybe. That's good enough, right? Now, what's the imaginary part of this thing over here? Well, this is equal to k times x plus iy. And so this is kx. Let's assume that k is just a real constant over here, right? If k is real, plus kiy. And so that says your streamlines are what? Streamlines are just going to be the imaginary part of g is constant. So your streamlines are going to be gamma sub c. And those are the points sets of z such that the imaginary part of g of z is a constant c. Okay? Good? And so, of course, what happens here, in this case, what do we say? This is the same as saying it's the set of all points. What? It's the set of all points k, k times y, such that y is a real number, right? Good. And so those are, and it equals what? ky equals c, of course, right? So we're going to put equals c in here. Equals c, ky equals c. Okay, y and r. And what are these lines? These are just horizontal lines. So how does this flow work? This flow corresponds to the situation. I have the complex plane, here's my x-axis, here's my y-axis, and then your streamlines are just this. Your streamlines are just the y-axis. There's my streamline, there's another streamline, there's another streamline, another streamline. And that should make sense too. That's just a perfectly reasonable elevator, right? And sure, an elevator goes this way, right? Easy peasy, right? You're at the airport, step on the walking platform, you move. That's a very good example of a flow, right? Step on the elevator. If you're lazy, unlike me, you don't move. I'm running down the elevator. I'm always in a hurry to get things done. Okay, good. Because the faster I get to my plane, the faster I can pull out a math book and start reading it, right? Think even from that perspective. The faster you get in that airplane, the faster you open your bag, get your math book out and start reading, right? Excellent. And then the people next to you on the airplane will say, what are you doing? And you say, would you like me to explain math to you for the next 4 hours? And they'll say, no, it's beautiful stuff. You should really do this, right? Good. All right, let's do the next example. The next most elementary example, actually. Let's suppose that g of z bar, this has to be holomorphic, right? Is just plain old z, okay? Then what's the complex potential? Then g prime of z is going to be z squared over 2, okay? Which is what in real imaginary parts? This is going to be what? This is going to be just x squared minus y squared over 2 right? That's the real part. The imaginary part is just going to be an I times xy, okay? Good, so what are my streamlines? The streamlines in this case, gamma c, are just going to be the sets of points x and y, such that what? Such that x times y is equal to c. Oh, those are what? Those are hyperbolas, right? Excellent. So what does this stream function look like? This stream function looks like the following. Here's the x-axis, here's the y-axis, and you have these type of flows. These are called flows around a corner, actually. What am I doing with these things over here? I'm really taking the upper half space of this guy and compressing it over there. And so we get a saddle dynamic over here for this flow. Like that, okay? I'm probably getting the arrows wrong. I always get the arrows wrong because I'm not a differential geometer, right? We can figure out the orientation later. Good. How can I have proven this directly? What's the direct ODE proof? Here's the direct ODE proof of this fact. It's a linear dynamic, right? So what do I have? I have the velocity field, dx dt, plus I dy dt, has to be equal to what? It has to be equal to, I said it was z bar in this case, right? So this is going to be equal to just an x minus iy. Cool. So x of t, so dx dt is equal to x, and dy dt is negative y. That's a linear system of ODEs. We know how to solve linear systems of ODEs. How do we solve that? Well, of course, this says that x of t is c1 e to the t, and this says that y of t is a different constant. They're decoupled, right? So this is the exact trajectories we get over here, right? Good. And of course, we know that the origin is a saddle, right? That's a saddle point. That's a saddle dynamic. Okay. And of course, if we multiply x of t and y of t, what happens? X of t times y of t. What has to happen over here? X of t times y of c, I've limited the parameter, just c1 times c2. Oh, lo and behold, what is it? X times y is a constant. X times y is a what? A constant. So the ODE is consistent with the complex procedure. Excellent. Okay, the ODE procedure is exactly consistent. Now I'm in a great shape. Pick your favorite holomorphic function on a particular region, right? And so now, of course, you can say, what if I have like a region that has lots of what? Lots of like bends, like you're trying to like pump water down a pipe that has lots of bends. You can figure out the streamlines of that by using things called Schwarz-Christoffel methods, which we're going to study in further videos, right? And how do you handle things in polygons, degenerate polygons, things like sine, things like cosine, things like x squared, things like x to the fourth, different streamlines. So for different holomorphic functions, you get different streamlines in different regions of the complex plane. Absolutely beautiful. As I said, this is actually called flow around a corner. This is flow around a corner. Okay. And that should sort of make sort of sense too. It's like if you ever tried to like put like water around like a bend, you'll see it sort of traject like that. It makes some sort of sense, but the key thing here is that what we want to do is we want to say, it's oftentimes easier for me, you say, well, wait a minute. If I have a very complex nonlinear system of ODEs, in some sense, I might be able to solve that. How? By trying to identify with a holomorphic function, so turning this two-dimensional dynamics into a one-dimensional complex dynamic. That's a very important technique in complex variables and in terms of differential equations, in terms of dynamical systems. If I have a dynamical system that has the right structure, I can think of it as a holomorphic flow. If it's a holomorphic flow, I'm able to use complex analysis to analyze the situation in a much more efficient, much more beautiful way, right? So in other words, I could take a very complex nonlinear system. If it has the right form, it has the form of a incompressible, so I keep saying incompressible, that's the fluid way of saying it, sourceless and irrotational flow, then if it has the right structure, I'm able to take that regular complex nonlinear dynamics and turn it into a one-dimensional holomorphic, single variable holomorphic complex dynamics, which oftentimes is just much easier to handle and a very, very useful tool when you're studying these problems. Thank you very much.